Forces are acting on us all the time through everything we do. Of particular interest might be the forces involved in our preferred sporting and leisure activities. Controlling and interacting with these forces is what allows participants to have fun in these activities. This lab takes a look at the forces involved in one skateboarding activity called dropping in. During this activity, a skateboarder drops from the top of a curvilinear surface and travels across that surface with gravity. With some information about the skateboarder and the measurements of the obstacle being ridden, the forces of the maneuver can be calculated. Gravity, as we experience it, is the downward force on an object due to its mass. Skateboarders work to control maneuvers coordinated with the force of gravity. Gravitational potential energy is the energy of an object resting at height. Kinetic energy of an object is the energy of that object in motion. Skateboarders travel up and down obstacles through most of their maneuvers, exchanging energy and feeling different forces. An object's velocity is its displacement over time. Centripetal force is the force toward the focal point of a curve that diverts an object's tangential path of inertia. As skateboarders travel through the curved surfaces of skatepark obstacles, they generate extreme velocities and navigate various centripetal forces. For this project, we need one skateboarder. The skateboarder must, of course, have one skateboard. The skateboarder must perform this maneuver on a curved skateboarding surface of known height and radius. One video camera is necessary for capturing the action at a known frame rate. There should be a tripod or a friend with a steady hand to hold the camera, making sure to capture all of the action. This project also requires one scale or similar tool to weigh the skateboarder and the skateboard. The first step in the procedure is to set the camera to capture the action. It is important that the camera is positioned to show the entire maneuver from the highest point to the lowest. The skateboarder uses his or her skateboard to drop into the obstacle and ride through the curve. It is important to note that the skateboarder dropping at the top of the ramp is the point at which the assumed system's total energy is potential, and the end of the traveled radius is where the assumed system's total energy is kinetic. The camera captures the motion, and calculations begin by analyzing the video. The time the skateboarder spends traveling through the curve is calculated by counting the number of frames and dividing by the video's frame rate. The distance the skateboarder traveled through the curve is calculated using the known height and radius of the curve. These figures allow us to calculate the skateboarder's average velocity, velocity at given points, acceleration, and the forces acting on the skateboarder throughout the maneuver. Centripetal force acting on an object through a curve is equal to the object's mass times the object's velocity squared divided by the radius of the curve. We'll take the skateboarder's mass with the skateboard together. The skateboarder's weight with the skateboard is 158 pounds, or approximately 71.7 kilograms. The skateboarder's average velocity can be found by measuring the distance traveled and dividing it by the time of travel. Since the skateboarder's riding surface is theoretically 1/4 of a full circle or loop, the curvilinear distance traveled can be calculated by plugging the obstacle's measurements into the formula for 1/4 the perimeter of a circle. Then, since we know the obstacle is 1 vertical foot taller than its radius, we add 1 foot to the previous total for the total distance traveled. The time of the skateboarder's travel in this case is calculated by the number of video frames captured of the dropping skateboarder from the top of the curvilinear surface to the bottom. The top of the transition is fairly obvious as the edge of the simulated pool structure, and the bottom of the transition is conveniently marked by a division and color change of the concrete. In this case, the skateboarder traveled for approximately 22 frames from the top to the bottom at a frame rate of 29.97 frames per second. The radius of this obstacle surface is known to be 9.5 feet. The height of this skateboarding obstacle is known to be 10.5 feet. Plugging into the formula for 1/4 of the perimeter of a circle, the curved portion of the riding surface is calculated at 14.9 feet, or approximately 4.5 meters. Adding 1 vertical foot for the total distance of the ridden surface yields 15.9 feet, or 4.9 meters. "22 frames divided by 29.97 frames per second equals 0.73 seconds of travel. With our measured distance and calculated time, the average velocity is equal to 6.71 meters per second. From the calculated average velocity and a known initial velocity of 0, we can calculate the final velocity with the known formula. Using the formula for average velocity, 1/2 times v1 plus v2, we know that the final velocity equals 2 times the average velocity when the initial velocity equals 0. The skateboarder's calculated final velocity is 13.42 meters per second. Using our average velocity in the formula for centripetal force, we calculate 1,113.18 newtons to be the average force on the skateboarder through the drop-in maneuver. The maximum force on the skateboarder occurs at the bottom of the radius, where the kinetic energy is at its maximum. Therefore, the maximum force on the skateboarder is the centripetal force at maximum velocity plus the force of gravity on the skateboarder's mass. Plugging our final velocity into the formula for centripetal force and adding the force of gravity on the skateboarder, we find that the maximum force on the skateboarder was equal to 5,155.39 newtons. Plugging in our final and initial velocities, we can also measure acceleration. Acceleration is equal to our final velocity minus our initial velocity divided by time. Dividing 13.42 meters per second by 0.73 seconds, our acceleration rate is equal to 18.4 meters per second squared. Gravitational potential energy is equal to mass times gravity times height. In our case, gravitational potential energy is equal to 2,248.5 joules. Kinetic energy is equal to 1/2 mass times velocity squared. Kinetic energy in our experiment equaled a maximum of 6,456.5 joules. With the known measurements of the skateboard obstacle and the time of travel from top to bottom determined by the number of video frames, the average velocity of the traveling skateboarder was calculated to be 6.71 meters per second. Using the average velocity, the average centripetal force experienced by the skateboarder was determined to be 1,113.18 newtons. With the average velocity and the initial velocity known to be 0.0 meters per second, the final velocity was calculated to be 13.42 meters per second. With the final velocity, a calculation of the maximum force experienced by the skateboarder, which occurred at the bottom of the radius, was calculated to be 5,155.39 newtons. The skateboarder's acceleration rate, which was determined to be 18.4 meters per second, was also calculated by using the final and initial velocities. Finally, initial potential energy was calculated at 2,248.5 joules, and final kinetic energy was calculated to be 5,456.5 joules. The speeds involved in this skateboard maneuver are relatively high, translating to a maximum of over 30 miles per hour. The varied calculations of forces are due to the curvilinear nature of the riding surface and the exponential introduction of forces over time. At the instant of onset of the drop-in maneuver, it can be assumed that no forces are being experienced by the skateboarder. And forces are increasingly introduced as he or she travels down the radius. This accounts for why the average force experienced by the skateboarder is only about 1.5 times the gravitational force alone. Gravitational forces are not fully experienced until the bottom of the radius. Calculations of the final velocity and acceleration rate above that of the gravitational acceleration alone can be attributed to the additional forces in the skateboarder's legs that increase pressure against the curved surface, which in turn increase speed, acceleration, and centripetal force. For this same reason, gravitational potential energy is less than the total kinetic energy calculated at the end of the radius. Actions of the skateboarder's legs led to higher than gravitational velocity. In future trials, inanimate masses can be substituted for the live skateboarder to control for the variable of muscle reaction during the drop-in maneuver. The measured differences can be compared to isolate the values of force and energy added by the skateboarder's muscle reactions.